at the end. Feel free to ask questions during the presentation. If you have time to stay on afterwards, I can answer questions then, or you can shoot me an email or give me a call sometime. Okay, let's get started. Get my window out of the way here. Let's see. All right, so today I'm going to be talking about the Lucky Mute NetMap project. We have this fancy title here, the Watershed Restoration Prioritization using Finescale Modeling and Field Verification. So just a quick layout of the presentation. I'm going to give a little project background, introduce what NetMap is, and the tools and analyses associated with NetMap, then go into how the Lucky Mute's using NetMap to prioritize projects, and then our next steps with this project, where it's not a complete project, so we're still working on it. So just a little background on the Lucky Mute. It's a tributary to the Willamette on the west side of the Willamette. For this project, we're really focused on what we call our model watershed. This area was delineated as the model watershed for the Lucky Mute. It's part of a larger model watershed program, but in this particular model watershed, it was picked out as a kind of key focal area because it has relatively productive wild steelhead run. We also have coho and lots of cutthroat. I say relatively because we don't get the production that we would get from some of the tributaries coming off the Cascades, such as the Santiams and maybe the Middle Fork Willamette. But in the Lucky Mute, this is a highly productive area. This is also a program that's in the BEF Model Watershed program. It's supported by Meyer Memorial Trust and OWEB SIP funding. This area, even though it has a high production of steelhead, cutthroat, and coho, it is historically splash dammed. You can see all the little dots there on the map, all the areas where we had large splash dams turn of the century. There's been historical removal of large conifers in the riparian zone. In some areas, the channel has been straightened, particularly along the upper main stem. Let me get my highlighter here. So this area, there's a berm built to build a railway, essentially. So that's led to a series of impacts, pretty common for watersheds in the Willamette. We've got a lot of incised channels, loss of floodplain connectivity, exposed channel bedrock. A lot of the splash dams, when those dams were released, it stripped away a lot of the good substrate in the channels. And there's an absence of large woody debris in the channels. These are all factors limiting recovery of the Lucky Mute. And in addition, we have kind of the normal issues that we have to deal with, such as just recruiting landowners, getting landowners on board. And then we have this increasing competitiveness for grant funding. There's more folks that are proposing great projects, and so we're having to be a little more strategic in how we're prioritizing and proposing our projects. So there's a number of different prioritization strategies. I won't really get into them, but it kind of starts with the opportunistic. You have a willing landowner, and you propose a project with any willing landowner, all the way to getting much more refined using modeling tools and field verification to prioritize projects using sort of decision trees, decision support tools to determine which projects are the best projects to work on, which are the projects that are more likely to get funding. You have kind of that justification, and you're able to answer that question of, why here and why now. So some useful information for addressing limiting factors and for prioritizing fish and temperature data, floodplain data, riparian re-veg data. Habitat intrinsic potential often is important, knowing where fish are likely to show up or your other focal species are likely to inhabit. So NetMap, the NetMap virtual watershed, it provides a lot of that data in one sort of user-friendly platform. Links spatial patterns with geomorphological processes. You can run comparative analysis on different data sets. You can customize the tools and do your own and customize your analyses, basically. You can become the modeler, something that wasn't very obtainable, achievable without having a lot of background knowledge and education specific in modeling. And it's not really too cost prohibitive. Again, much different than it in years past. So we decided to go in for an OWEB technical assistance grant to obtain NetMap for the LECUMUTE with the primary goal of prioritizing a list of projects to address those limiting factors that I discussed, primarily due to historical splash damming in the LECUMUTE. We wanted to convene a technical team to just advise us on maybe the direction we should be taking, what things we should be prioritizing. Then develop a list of prioritized projects to field verify, which we would send our fish biologists to do, and then use, at least turn a couple of those prioritized sites into project design so that we could follow up and do some sort of either restoration proposal to OWEB or some other funder. That totaled to about a $46,000 OWEB ask, and then with some in-kind and cash match, total project cost of $66,000, which again, we saw it as a net savings as opposed to sending a fish biologist to all streams in the LECUMUTE to do surveys, which is also limited because they're getting an on-the-ground view, and you don't have a whole watershed view when you take that approach. So just currently, we've already obtained the NetMap tools, familiarize ourselves with those. We convened the LECUMUTE tech team and have had a couple meetings to determine what directions we should be taking with the tools. We've developed a list of prioritized sites, so we're just getting ready to send our fish biologists out to do some field verification. I'll probably tag along for some of those, and just got a contract together today, which is awesome. And then we'll still need to develop the project designs and submit our proposals, at least one proposal, likely the end of October. Okay, so what is NetMap in the virtual watershed? It sounds like something you might find in Star Trek, but it's something that we can use today, which is lovely. So this is sort of a condensed slide. I'll attempt to kind of explain the inner workings of NetMap. I'm sure there'll be questions later, but essentially it takes LiDAR data. So we submitted LiDAR to TerrainWorks, who develops NetMap, which LiDAR is sort of kind of a blanket of data across the landscape. It's a grid, really, and it contains information on elevation and drainage area gradient. They then use that LiDAR to determine flow direction. So the topography of the land determines your flow direction. That then drains into a channel. Flow directs towards a channel. So they're able to build a virtual stream network based on flow direction. So once they have that stream network, they then break up that network into several different reaches. It starts with like 5 meter, and then they build that up to 100-meter reaches. And there's nodes between each of these reaches that allows the virtual watershed to send information or data up and downstream on these channels. Each one of these 100-meter reaches are associated with a drainage wing. Let me see if I can get my pointer over here. Okay. So, you know, you have this flow direction. They're creating these channels, and these 100-meter reaches are associated with sort of like a mini sub-watershed. These are the drainage wings. So it allows you to associate things that are going on the land. They put like this bear kind of walking across the land. I'm not exactly sure how they associate bears with stream channels, but essentially you can look at things like, you know, erosion in your upper hill slope and how that connects down to your stream channel, and then you can route in that information up and downstream, and you can get things like floodplain width along several reaches. So that's kind of the basic background. One thing I'll say is that they use this LiDAR data and kind of add on to that statistical regressions. They're published models and regressions to include other types of attributes in the data set. So like intrinsic potential, there's published models on habitat intrinsic potential that they can include in the data set. So this is just a list of several of the attributes that come along with the data set. You can get gradient, elevation. Those are kind of the more simple attributes, all the way to the more complicated ones like floodplains, identifying terraces, identifying areas that are likely to erode and contribute high quality gravel, for instance. So for the LUCUMUTE, sort of the steps that we went through to develop that virtual watershed was we first submitted LiDAR to TerrainWorks. This was a 3-meter digital elevation model we obtained from our local BLM district. They then used that LiDAR to create the simulated stream network, or virtual watershed, and then they send that back to us to correct any inconsistencies in the stream network. In some cases, some of the channels can get routed down like roads or farm drainages, and so we kind of went in and found where those areas were and let them know that it looked like an error, and then we sent that back to finalize that stream network. And then they integrate other data sets on top of that. So we have 4 years of fish survey data that we submitted to them, and they were able to snap that information onto the stream network. There's several others, but another important one that we use is it's called Lemma. It's a vegetation data set out of Oregon State that gives you things like stand height and basal area across the landscape. So once they integrated those, and then they sent us the NetMap tools and analyses, and we did a webinar with TerrainWorks, kind of explained some of the background and just some of the tools and how to interact with NetMap. So this is essentially what we got. Our watershed was broken up into 3 data sets. They probably could have put it all in one, but there's tons of data in there, and to run some of the analyses, it takes a lot of computer power. So in order to make that a little more manageable, it was broken up into 3 different kind of watersheds here, and that essentially you can only run analyses on one of these at a time. But for us, it's worked out fine. You could request that they do the whole watershed in one, but I think you can kind of work around any potential issues that it might present by breaking these up. As I mentioned before, these were all broken up into 100-meter reaches, and we received this on an ArcMap shapefile, essentially. So here it is in ArcMap, and I'll just kind of show a little bit how you interact with the virtual watershed. You get this toolbar up here, which allows you to kind of manipulate certain things. the hillshade and some of these other attributes kind of come with the data set. So this is the attribute table of the data set. So you have, it's like I was saying before, it's all in one layer, and you have all the associated useful information, all the attributes in that shapefile, and you can open up the attribute table, and you see here you have a length of each reach. They're all virtually 100 meters long. You have like elevation, stream order, gradient, width, and so on and so forth. And then there are a number of analyses that they do for you, and they come into this this maps option here. So they'll run like a intrinsic potential analyses based on a published model on the Oregon coast. And you can just click on a map and it'll pull it up. And it's an easy way to just see some of the analyses and see some of the tools that you can then go in to manipulate in that map. So this analysis tools toolbar, it allows you to sort of run, what's the best way to put this? To kind of mine the data. It doesn't allow you to change the data, but really mine some of the data. So there's one here called risk analysis that I'll talk about later. One thing that's cool is you have this Google Earth option. So you might run an analysis like where are your streams that might be getting more solar radiation than others, and you can run that analysis, and then you click this Google Earth tool, and then it'll pull up that area in Google Earth and show the virtual watershed in Google Earth. So that's been pretty useful. We've used that quite a bit. And then this watershed toolbar, it allows you to run your own analyses and do kind of your own customized modeling in a way. You can enter in criteria and do like a customized habitat intrinsic potential, or look at things like floodplain width at certain bank elevations. Okay, so that's NetMap. Now moving, taking NetMap to our prioritization. These are the steps that we went through essentially to get there. First, we needed to determine our fish distribution. Where are our anadromous fish able to reach in the watershed? Then we wanted to establish our anchor habitats. We're taking the approach here that we want to find the best areas for fish in the Lucky Mute, and then either see what else we can do to improve those areas, or to just work out from those areas. So it's kind of the protect the best approach to restoration. And then we would prioritize reaches within those anchor habitats. So this is the fish distribution map that came with our NetMap. It's based on some generic criteria developed out of Alaska Fish and Wildlife. It basically just finds where you have gradient barriers and major either waterfalls or culvert perches where your fish aren't going to be able to move upstream. So there were a couple issues with that. We had to go in and fix areas where we replaced a culvert in the last couple years. And so, for instance, down here, we had a project on Price Creek, and fish distribution layer was stopping here, but we replaced this culvert.
seem to have lost audio. JP, are you there? Are you there, JP? Trying to fix it. Let's see. I'm going to try and unmute one of you and see what happens. Sorry about that. Cheryl, can I unmute you? Can you hear me, Cheryl?
I can.
Okay.
He got muted as a fish bearing stream.
Somehow JP got muted. Nope. Best laid plans, eh? Yeah. Can you hear me now, JP? You're gone. How about that? Can you try calling in, JP? Kristen?
So, okay, how about now?
Yeah.
Okay. We're back online. Okay, so the answer to your question, Sean, what did we used to do before we had this technology? Probably this didn't happen. Okay, I'll go back to fish-bearing streams. There's not a whole lot there except to know we needed to determine where our anadromous fish were in the watershed, and there's some tools to do this in NetMap. We kind of had a default setting that we wanted and tweaked a little bit so that we could kind of customize that a little better for the Lucky Mute. Okay, so again, moving into anchor habitats. What I was saying before is that we're focused on steelhead and coho recovery for this project, but we recognize, and it was pointed out in some of our meetings with the tech team, that we care about other ecosystem processes and benefits. And we're really just using steelhead and coho as umbrella species. When we propose projects, we propose them as steelhead projects. We're more likely to get funding that way, but we care about things like water storage and water quality and other wildlife benefits. Okay, so kind of drilling in here, how did we determine our anchor habitats? I started working here with our fish biologist, basically asking him where are the ideal areas in the watershed to where you would expect to find your steelhead or your coho based on his many years of experience. So his responses were, well, gradient's important, kind of threw out there 1 to 5%. We want wide connected floodplains. We started with 4 times bankful height, width of your floodplain at 4 times bankful height. We played around with that a little bit. So basically my job was to take his knowledge of where he thought fish would be and interpret that through NetMap. So this map here shows everywhere we have gradient at 1 to 5%. This map shows here anywhere that we have floodplain width at 4 times bankful height greater than 40 meters. So then in NetMap, I put those two together, and this was the result, which in a lot of ways it looked kind of it looked representative of what we know about the watershed, except that we have a lot of these main stem areas that are being highlighted and some of the lower watershed that we think is probably a little too warm for fish. So we added another criteria that was channel depth. So channel depth, any channel depth below 0.75 meters, it's about around 2 feet. And so now we're really kind of getting, we're trying to exclude those areas where we might have incised channels. Before, these were being highlighted where we have wide floodplains, but the channels are pretty incised. We have a lot of stream power coming through here, so we know they're not great for, it might be good for fish migration, but not good for rearing. So now we're really kind of drilling in those non-incised channels. Again, we have kind of these lower areas that are probably a little too warm for fish. So we added in our fish survey data, and that kind of pulled those out. And again, just kind of drilling down, getting to a more refined list. In some areas, we don't have fish survey data. And what we're really trying to look at here is temperature. So there's a tool in NetMap that allows us, it can't measure temperature, but what it can do is measure solar radiation that's hitting the stream channel. This particular tool, it looks at like the orientation of the stream, so solar exposure just based on orientation, and then it uses the lemma vegetation data to understand how much solar radiation is hitting your stream, and then it routes that information downstream. So it's sort of a cumulative effect as you move downstream, and you get a lot of kind of channels that are exposed to solar radiation. You know, it starts to warm up. And if you get another channel that's relatively cool, it may cool that back down. So what we found is that adding that analysis in, it was very reflective of when we added in our fish survey data. So you kind of go back and forth. They're pretty similar. So we thought that would be a pretty useful criteria to add into our anchor habitats.
JP, can I interrupt for just a second?
Sure.
Some folks may need to go, so I just want to open it up for a couple of questions if there are any. We want to give you a little bit more time since we lost a couple minutes, but
sure.
If folks have made other plans, let's just take a second and see if there are any questions.
Okay. Are we at the 30-minute mark? Oh, wow.
We are
yeah, that went fast.
Time goes fast, yeah. I'm not seeing any, so continue.
Okay. Yeah, we're almost done. I'll try and rush through this real quick. So there are some additional analyses that we could do. Right now, we're kind of leaving at those 4 criteria. But one that we're interested in using is this erosion potential. It looks at erosion potential in the watershed, and then routes that erosion potential down to stream channels. So where are the stream channels likely to receive substrate and gravel, essentially. We can then overlay that onto our anchor habitats and see where at our anchor habitats that erosion is being routed to. And so those might be areas that are likely to recruit high quality gravel, good for spawning fish. There's a number of other analyses, but I'll skip over those. We're not running them now, but we may consider them as we're kind of moving forward. Okay, so this is the last kind of major section here. So taking our anchor habitats, we then want to prioritize our reaches. There's a few different ways you can do this. You can look at all the different analyses individually and just kind of put these maps up on a wall and maybe highlight some areas that that are showing up as kind of your hot spots. But there are tools in NetMap that allows you to kind of mine the data and put different analyses on top of each other and spit out where those priority sites are. So for instance, you can use your habitat intrinsic potential and overlay like that erosion tool and say I want areas of high intrinsic potential and areas likely to give you good gravel supply and then it'll overlap those analyses and give you your priority sites. Basically, what we're doing is we're taking the intrinsic potential tool and prioritizing within that. So we have our criteria here. We've also included fish, which isn't being shown here. But then we can set kind of ideal windows within each of those criteria. So we said 1 to 5%, but really 1.5 to 2.5% is sort of the sweet spot within that reach gradient. That then gives you a curve, which you can see using this tool. You can see it here. This is 1 to 5 here, with the 1.5 to 2.5% being ideal. So I can do that for each of the criteria and set these kind of ranges and curves, and then it'll kind of quantify which are the best reaches using that criteria within our anchor habitat. So you see the red here are our high-ranking reaches that have a number. It's a quantified measurement associated with them. You can also then, in our case, we took this kind of customized intrinsic potential or anchor habitats, and we can run this tool that will find the top percentage sites within that tool. So here I said find the top 50% within our customized habitat intrinsic potential or anchor habitats. And then it further kind of drills down and picks out those reaches that, maybe the reaches we want to go out and field verify. You can do that with several other analyses. You can say top 50% of habitat intrinsic potential, and we've included fish in our habitat intrinsic potential, but here I have it as separate. You could use like erosion potential, for instance, and say we're the top 50% of erosion potential areas and overlay that with your habitat intrinsic potential. There's, again, the result of that. So we've taken these top reaches and we have a kind of a rank associated with them, determined based on our customized habitat intrinsic potential, and we're able to prioritize because we have that quantified number associated with each of these reaches. And so we've now generated a spreadsheet list of all our anchor habitats and have ranked them all, and we're getting ready to send our field biologists out to field verify these in the order that they rank. One other thing you can do is you can kind of lump these in sub-watershed. So what sub-watershed are you getting the most high-ranking reaches, and it kind of lumps these together. These are pretty reflective of what we expected. Reset there somehow for some reason. Skip through this. Sorry about that. Okay, so that's pretty much where we're at in the process. Next steps are to field verify, then develop the project designs, submit the project proposal. Just some other analyses we're interested in doing. We're actually starting to work on a shade analysis that will basically will look at how much solar exposure we're expected to remove from entering the stream channel based on previous project that we've completed. Once we get those numbers, and we can kind of promote that as, this is the work that the council has done to remove solar energy from hitting the streams and essentially cooling down stream channels or slowing down the rate of warming, depending on how you like to look at that. We were interested in doing some beaver habitat analysis, identifying this historic beaver habitat and identifying beaver habitat potential, so intrinsic potential for beavers. And we'd like to do a timber area roads analysis to identify areas where we might that might be contributing excessive sediment to the stream, and working with our timber partners to mitigate that impact. Then just some final closing comments. If you're looking at maybe doing something like this for your organization, just be aware there's a big time investment just to orient with the NetMap tools. There's a lot of functionality and a lot of things you can do and it's easy to fall down a rabbit hole if you're not real clear with your objectives. It's good to take a collaborative approach if you can. Ideally, I think if you have one, if convening the tech team has been really helpful to help just advise us on what what are our key criteria that we want to focus on, but also I think in an ideal situation you have one power user and then several organizations that are able to work with that power user so that they can produce analyses for them without each individual organization having to know how to work and use the tools. It's good to have on-the-ground knowledge so you can kind of verify that the results you're getting are reflective of what is actually out there, at least of what you know about your watershed. And as I mentioned, clear objectives are pretty important. So that's it, just some acknowledgements. Sorry I ran over. If there are any questions, I'm happy to answer them.
JP, you had a slide, I think, with your email address on it, did you not?
You know what? Not sure if I did, but let me put that up. I forgot to.
Or you can just say it and folks can write it down, maybe.
Yeah, or I'll send it in my chat box here.
Okay, great. Super. Okay, if anybody has questions, feel free to just raise your little icon, hand icon, and we'll call on you. I know some of you need to run, but before you do, I want to just thank JP for taking the time to do this and for Kristen for setting this up. And we'll stay on for a couple more minutes in case people have questions, and folks can follow up with you afterwards.
Absolutely.
Yeah. You all will receive a notice that this has been recorded with a link to it. So if you want to share this with anyone else, feel free to do that. And if you also want to give a webinar, this is a chance to do a show and tell with your colleagues. If you want to share something that you're working on, a tool or some lessons learned, either in the administrative part of your job or in the technical part, by all means, this forum is available for you to do that. So, okay, I'm not seeing any questions come in, JP, so we'll just end here and thank you again. Thanks, everybody, and you'll be getting an email from us.
Sure. Thank you. Bye.